Hi everyone, today we are going to talk about my thesis, compositional value-based methods for planning and generative modeling. As an overview, we will first talk about the motivation, and then we will talk about the framework, the application, and finally the discussion. Here are the references for this talk, and basically they are just papers, and feel free to read them. In the early days, the AI is defined as a conjecture. The conjecture is that every aspect of learning and intelligence can be in principle be precisely described, and it can be so precisely described that a machine can be made to simulate it. Nowadays, the definition of AI is a little bit different. People use data-driven approaches to learn this kind of behavior of intelligence directly from data. And today's Oxford English Dictionary just defines AI as the capacity of computers to exhibit or simulate intelligent behavior. The exact definition of the intelligence does not exist anymore. But why does this happen? Why we change from the early days AI definition to this modern days data-driven approach? Obviously, there exist several bottlenecks for symbolic AI which might drive this transition. First bottleneck is that we need to hard code all the domain knowledge for symbolic AI. Another bottleneck is that when symbolic AI meets novel input, there might exist a brittleness, which means that it cannot generalize for this novel input. The final bottleneck is that the combinatorial complexity in the real world. When there exists a combination of the complexity in the real world task, the symbolic rule-based AI might not be able to organically organize its symbolic rules together to deal with this complex task. For the data-driven AI, it directly learns domain knowledge from massive amounts of data, which circumvents the bottleneck to hard-code all the domain knowledge. Another way it solves the brittleness for novel input is that it measures the generalization on the test dataset. So now it has a way to measure how does it generalize. But there still exists a big question mark whether these modern data-driven AI can generalize to combinatorial complexity in the real-world tasks. As an example, here we try to figure out how does it deal with the combinatorial complexity on an image generation task. So I first asked ChatGPT to give me, for example, 20 kinds of the animal names. And then based on these 20 names, I then asked ChatGPT to draw an image that includes all these animals. And I gradually increased the number of the animals to draw on each image. Left is 20, in the middle it is 40, on the right it is 60. And then as the task gets more and more complex, we can see that there exists some unnatural combination of the animal parts. For example, in the middle you can see it seems to try to draw a camel, but instead its head is a very strange head. And then for this one there is a combination between the snake and the octopus, which is very unnatural for the original animal that the ChatGPT tries to draw. It seems that it cannot really generalize very well to more and more complex tasks. And our way to deal with this combinatorial complexity is to bring the compositionality to the AI system. And here we investigate into 4 applications which include motion planning, multi-agent planning, multi-agent CV navigation, and image generation. The core of our approach is called compositional value-based methods, which is using value functions that can be modularly combined to solve more complex tasks than those seen during training. A formulation is like we can take an input or part of that input to a value function, and then this value function, typically a neural network, can give us a scalar value. We investigate into 2 frameworks. The first one is compositional input, which is we call implicit compositionality, where the input can be composed of a variable number of the elements, and each element we call here as a sub-input. Given this series of sub-inputs, we feed them together into a value function, and then this value function gives us a scalar value. The second framework is called compositional value output, where we call it as explicit compositionality. So for each part of the input where it is different parts of the sub-input. We feed them individually into a value function, and then that value function will give us a series of values corresponding to each of those sub-inputs. And then we will compose these values together into a whole scalar value. For the compositional input, we rely on the compositionality of the input itself. So for example, the input here can be graphs or a sequence of tokens. And then we can feed this graph or the sequence of token to a value function which takes a variable number of the elements, typically a graph neural network or transformer. And then this value function will give us the value output as a scale value. Here, for example, it can be a heuristic value. Under this framework, we investigate two applications. One is the motion planning, another is the multi-agent planning. Another framework is the compositional value outputs. So for example, the input here can be a constraint, and then the value function will give us a feasibility score regarding this constraint. And then we simply take the min or max operator over this bunch of the values, which gives us the final value output. This value output typically represents how this input can satisfy multiple constraints. We investigate two applications as well. So one is the multi-agent sim navigation, another is the image generation. So we'll first talk about the compositional input and then the compositional value output. Let's start with sampling-based motion planning. So sampling-based motion planning is typically a problem where I'll give a start configuration and a go configuration. We want to find a path which is collision-free that can lead us from this start configuration to the go configuration. Here in this example, a start configuration is a 7-dimensional vector. The go configuration is also a 7-dimensional vector, and each element in that vector represents a joint angle on this robot arm. Collision-free basically means that we want a path without colliding with this obstacle. And we use graph neural network as a generalizable graph heuristic to guide the search for this graph problem. So basically it is like the graph planner, which here it is a best first search, will ask the graph neural network which edge is the best to prioritize its exploration of to search the feasible path on this graph. And then the graph neural network here, for example, it will correspond, the pink one will be the highest, most possible promising one among these three edges. And then the graph planner probably will take its suggestion and then prioritize the exploration of this pink one in comparison to the other candidate edges. So the graph network basically takes, for example, the whole graph and optionally the representation of the obstacles as inputs, and it will output a scalar value for each edge on that graph as a heuristic value. We will let this heuristic value by imitation learning. So basically it is using expert planner, which here it is a Dijkstra planner, and then it will take this whole graph and then give us collision-free path from this start configuration to the go configuration. By imitation learning loss, we mean that the graph neural network will try to make sure that the heuristic for the edges on this path to be higher than the heuristic for the other edges on this graph. If it can do that, then probably it will also guarantee that the exploration on these edges is prioritized in comparison to the exploration of the other edges. We did a generalization test to see whether this graph neural network can generalize the exploration on edges between different geometry of the environment. So here we try to prioritize the exploration of the edges in maze problems, and for the difference between the easy ones and hard ones, it is basically a block is missing in the maze for the easy task, while the block exists for hard task. And then you can see that the GNN can generalize by finding a feasible path for both of these two environments, while next, which is another learning-based planner, will typically fall at the local region when tries to explore which edge is the promising edge during its exploration. Another example is the robot arm example, where the difference between the easy environment and hard environment is basically two blocks exist for the hard ones. You can see a similar pattern here where the GNN can help us find a feasible path, but the next, which is a learning-based planner, will stuck at the local region when trying to explore. We did our experiment over 6 different kind of the motion planning environments, and then we see that in general, the graph neural network can help us maintain a relatively good success rate, also relatively low collision check and a pass cost. We also did a generalization test to see whether this graph neural network can generalize to different number of the elements in the probing samples, which basically means the number of the graph nodes in a graph. We can see that ranging from 200 graphs nodes to 1000 graph nodes, the graph neural network can basically maintain a relatively high success rate. A limitation here is that when the probing samples gets much fewer, which basically here it is like 50 nodes or 100 nodes, the number of the success rate will drop relatively significantly. This means that since we are still relying on the implicit generalization of the graph neural network, when the training distribution and the test distribution has a very huge gap, the OOD problems still occur for this kind of the tasks. We extend our idea to 2 different domains. One is the dynamic motion planning, another is the multi-agent pathfinding. Here I will briefly talk about the multi-agent pathfinding problem. So here we also model the MAPF, which is multi-agent pathfinding, as a search problem. So basically, for this search problem, the path planner will first start from an infeasible solution, and then it will search what kind of the conflict it will solve first during its search process, and then hopefully at the end it will reach a feasible solution. And since it is a search problem, we use a graph transformer to guide the search during this search process. The graph transformer also takes compositional input, which here it is both the task graph, which is the graph each agent will perform the path planning on, and also the temporary solution from all the agents. Here we call it as the tokenized agent path. We'll feed both these 2 inputs to the graph transformer, and the graph transformer will give us a heuristic value for the current temporary solution. We also did some kind of a generalization test for these 2 environments. One is the maze environment, another is the box environment. For the maze environments, we train the graph transformer between 2 agents to 10 agents and try to see how it generalizes to more agents, for example 26 agents. For the box environment, it's like between 2 and 4 during training, and we try to see whether it can generalize to 10 agents. The green curve here is the variance of our method, and the blue curve is the classical path planner, which is the ECBS. The red one is the CBS, and the orange one is the ORCA. We can see that our method can, in general, generalize better than the other methods regarding more and more agents during testing. So as a midway summary, we can see the compositional input assumes that the input itself is a very structured one, for example, the graphs or the tokens. And we require a specialized neural network architecture, for example, the graph neural network called the transformer, to deal with these structured inputs. To some extent, the neural network itself can generalize the performance. For example, given more elements, probably the success rate will remain basically the same and will not like drop too much. But when the number of elements is very different from the one during training, then a limitation still exists. So if it is still a out of distribution problem happens when these kind of the elements are very different from the training graphs or tokens. And we try to avoid this OOD problem with compositional output. So basically, we will also investigate this kind of the compositional output into 2 applications. One is the multi-agent safe navigation, and another is the compositional image generation. So first, for the multi-agent safe navigation, it's trying to satisfy 2 objectives. One is there should be no collision during its navigation, and then finally the agents should reach a goal which is in advance designated. And then we also want to see a generalization behavior. For example, if we train the model between 3 and 8 agents, we want to see whether it can generalize to more agents, for example, 32, 256, and 1024 agents. Our key approach here is to decompose those relatively dense graphs during test to those relatively low density graphs during training. For example, when the number of the agents gets more and more during the test, it is highly possible that the graph will be very different from the training. The main reason is that the neighbors will get very dense during the test. Our approach is like decompose this graph into those graphs that the model has seen during training. We introduce a technique called graph decomposition, which is basically decompose this graph into a bunch of subgraphs. And for each subgraph, we make sure that the density of that subgraph is basically similar ones as those graphs during training. For each graph, we'll try to sample a bunch of neighbors in this original graph, and then once the density has reached a maximum, then we'll stop this sample and continue to sample the next subgraph. We'll stop this iteration once all the neighbors are covered in these subgraphs. And then for each subgraph, we'll use a learned model, which we call here a control admissibility model, to try to predict for each action whether that action can lead us to a safe situation based on these surrounding neighbors. So for example here, if this agent takes an action that can lead to this purple neighbor agent, then probably its corresponding model will predict a negative value for that action. For all the actions that can lead this agent to the safer places, for example, these blank region, then probably the control admissibility model will predict those actions have a positive value regarding these actions. So basically here, a positive admissibility score means a feasible action, and a non-positive value may mean a infeasible action. And we can try to understand it from the landscape of these values. For example, here, among all the actions, it will form a landscape over the feasibility scores. And for the values above 0, it will basically mean the feasible action. And for the values below or equal to 0, it will basically mean the infeasible actions. And then basically each graph will kind of represent a constraint for what kind of the action is safe and what kind of the action is not safe. So there exist multiple kind of the constraints, and for each constraint we'll have a kind of the landscape for the feasibility. And then we'll try to compose these feasibility landscape into a composed feasibility landscape. And for this composed feasibility landscape, it is basically taking the minimum over all this landscape regarding to one action. For each action, it will have a composed feasibility score. Then for those actions which has a composed score beyond 0, it basically means a safe action. For those actions that are non-negative, probably it means an infeasible action. So this kind of composed score will represent a feasibility score for the original composed graph, usually to like all these subgraphs must satisfy the constraint. We learn this value function through a control theory inspired labeling. It is trying to see what kind of action will lead the agent eventually into a unavoidable collision in the future, and if it will lead to that collision in the future, then probably the value function should predict that action as a dangerous action to make sure its value is below than 0. Otherwise, it might be a safe action and then the score will be a positive one. As we said before, we'll compose these feasibility values together and then basically see what kind of actions itself is a safe action by inspecting it and comparing the feasibility score with 0. Among these safe actions, we'll see what kind of action can lead the current agent to the closest to the goal among these safe actions. We also did some generalization tests regarding the number of the agents. So for example, in the car, we'll train the agent between a number of 1 agent to 8 agents during the training environments. And then we'll see whether the model can generalize to 512 agents during the test. So our method here is the blue line here. We can basically see it remains a relatively well safety rate regarding the number of the agents from 1 to 512. This is basically because we decompose our unseen graph during test to those seen graph during training. So the OD limitation will be mitigated during this graph decomposition technique. Here is basically a video showing how this control admissibility model can generalize to very impressive number of the agents. And then later we kind of extend this idea to image generation. So here still we have different kind of the constraint. For example, we want an image to include a robot, to include a sunflower, to include a lake. Then the composed prompt might be a robot holding a sunflower beside a lake. Sometimes the diffusion model will correctly recognize all the objects in the prompt and show an image that contains all the prompt. But sometimes, for example, a stable diffusion model will miss some object in this prompt, only show the robot and the lake. The sunflower itself is missing in its generated images. As an illustrative example, we also show 2D compositional diffusion generation example here. So for example, we can have different algebras, for example, product, where the ground truth 2D samples must come from both of these 2D distributions. A mixture, which basically means the sample can come from either of these two distributions. The negation, which means that the sample should come from this distribution and not come from this distribution. To suit a baseline composable diffusion, where you can basically see that there exist some samples that really do not belong to the ground truth. We call these samples as the samples that has relatively low density in the target distribution. And our idea is to reject these samples after the samples are generated and try to eliminate them using the rejection criteria. And the question is like how to devise a rejection criteria that can correctly recognize these samples and maintain those samples that are correctly in the target distribution. We introduce a concept called the lift, which is a existing concept in the data mining back to 1997. So it is basically comparing the conditional density to a unconditional density. So here X might be a sample to generate, for example, the 2D point of the image. The C represents a constraint to satisfy, for example, the 2D component distribution or an object to appear in an image. And then we kind of compare this conditional distribution for this sample under C to a unconditional distribution for the samples. And we say that when the lift score is beyond 0, then it means the sample itself is aligned with the condition C. But if this lift score is non-positive, the sample itself is misaligned with the condition C. As a illustrative example here, the blue line is the density curve for one conditional. So which basically means Px given C1. C1 is the condition here. The green curve is the unconditional distribution's density curve. So as you can see here, when the lift score is exactly 0, we draw a right dotted line that separates the samples that we need to reject and the samples that we need to accept. For example, for the samples that we need to accept, the conditional density is higher than the unconditional density. We also show in the paper that we do not really need to train an additional value function to estimate this lift score. We can directly use pre-trained diffusion models to estimate lift score, which gives us a lot of convenience because we can now scale up this method to, for example, image synthesis task because we do not really need to train those large models by ourselves. We can directly utilize pre-trained models. As an example here, given this image, we will separately estimate its lift score given different parts of that prompt. For example, the robot the sunflower and the lake. And for each part of the prompt, it might represent a constraint to satisfy for the lift score. For example, the lift score for the robot here is 0.7. For the sunflower, it is negative 0.3, and for the lake, it is 0.6. And then after we get each individual lift score, we'll compose them together into a composed lift score by basically taking the minimum over these lift scores. So for example, here it will give us a negative 0.3, and since this score is a negative value, we will reject this image because now it is misaligned with the prompt of the sunflower. We did a sanity test to see whether this method can align with the condition in 2D compositional generation, and we can see that our method can correctly reject those misaligned samples and keep those aligned samples in this 2D task and correctly give us an empty set for this negation task. And we call this lift score as a compositional value function because now we can compose this lift score given a bunch of the condition to satisfy. We also scale up this method to the text-to-image compositional generation task. So for example, here the prompt includes two components, to draw and to appear in one image. Sometimes the Stable Diffusion XL will give us some images that do not really include all the objects to appear. As you can see in this example, our complete criteria will help us correctly accept those aligned images and reject those misaligned images. We also try to see some explanation from the physical meaning of this lift score in the latent space. So here, the activated pixel basically means that the pixel that has a positive lift score in the latent image. For those pixels which has a negative lift score, it is basically the black color. And then you can see that, for example, the lift score itself corresponds very well with the meaning of the object in the prompt. So this is the activated pixels for the glass bottle. This is the activated pixels for the starfish. This is a beautiful image where the activated pixels are for the stars in the original image. This is a numerical result to see whether plugging in our complete criteria back to the original diffusion model to see whether it can improve. By plugging in our complete criteria, sometimes the one generation of the Stable Diffusion can be better than the next generation of the diffusion model. Here are some more examples about what kind of the images will be accepted and what kind of the images will be rejected using our complete criteria. So as a midway summary, the compositional value output assumes that the constraints themselves are decomposable, and under some circumstances, we can leverage existing pre-trained model, represent them as the value functions instead of to train the value functions by ourselves. And we can also integrate these value functions with rejection sampling, but it still depends on the quality of the proposal distribution. As a final discussion, we want to talk about this philosophical question whether the scaling can replace compositionality. For example, some bro like me will think like we want to inject some human inductive biases into the model. For example, modularization, the logical reasoning, or the grounding in real-world communication, the social dynamics, which are the inductive biases from our designers of the neural network. And a bunch of the other people will think that simply scaling will help us learn this kind of compositionality naturally from massive amount of data. To think whether compositionality can be replaced by scaling, we need to understand what are the key ingredients for the compositionality. I call it the adaptive computation and memory. So for example, here the x-axis is the task complexity. In our study, we basically investigate into the number of the components in the task, but it surely can have different meanings. In the y-axis, it is basically the computation and the memory it needs to accomplish the task. A naive scaling law might say that the computation and the memory need to scale correspondingly to the task complexity. Similar things happen to the compositionality itself. So for example, in our study, we show that for a simple task, we can have small computation. And for the hard task, which includes more components, we might need more larger computation. We show this kind of the properties using either the search algorithm or the rejection sampling algorithm, accompanied by the learning-based value functions. What naive scaling can bring us is like a fixed budget regardless of the task complexity. And as you can see here, as the model gets larger and larger, it can solve more tasks. But for those tasks that require more computation and more memory, they still exist as infeasible and failed tasks. Obviously, some current efforts are there to solve this kind of the fixed number of budget, regardless of the task complexity, which includes, for example, the reasoning models, the chain of thought, or the coconuts, or like the retrieval augmented generation or web search. All of them are trying to inject more computation and more memory when the task gets more complex. But still, these kind of efforts seem limited by their training domain. For example, when the task gets more complex and so complex that it is very different from the training environment, the number of the computation the current efforts requires will go to explode. As a result, there still exists a wall where this method cannot go beyond, and there still exists an infeasible or failed task. We may need a system that can intrinsically expand, and in our study we show probably a promising way by bringing compositionality itself to the AI system. So as a summary, we show the compositionality via 4 applications and 2 frameworks. In the future, we want to understand when the compositionality is or is not useful, and if possible, we want to make a model that can automatically find the compositional structure. And sometimes when the task gets different during test, probably we need to continue learning to see what is a good compositional structure adaptively during test. Finally, I want to say thank you to a bunch of people, including Professor Gao, who is my mentor, my friends, my committee members, and my family. I feel so grateful to have this journey with you guys. Thank you so much.